right, so we are almost done talking about Taylor series, and we would be remiss if we did not discuss how to use these things in ways we never imagined. Let's make sure that we understand what the must-knows are. What are the series that you have to know cold from memory no matter what? Well, you have to know that 1 over 1 minus x is the sum of a geometric series. It's 1 plus x squared, and so on, where the generic term is x to the n, and that works on negative 1 to 1. That's the interval of convergence. So what does that mean? Well, that means that we know what 1 over 1 plus x is, because that's 1 over 1 minus x. So that's 1 plus a minus x plus a minus x squared plus dot, dot, dot. That's negative x to the n, dot, dot, dot. That also holds on negative 1 to 1. And why do we care about that? Because that lets us know what the natural log of 1 plus x is by anti-differentiation. So that's the antiderivative of this thing that you see, right? That's this. This also lets us know what 1 over 1 plus x squared is, because that's 1 over 1 minus negative x squared, and that's 1 minus x squared plus x to the fourth minus dot, dot, dot. The generic term is negative x squared to the n, and it goes on. And why do we care about this? Because it lets us know what the inverse tan of x is by anti-differentiation. And it goes. So this is a must know, and you've got to know how to get to these. That's for sure. What else is a must know? You have to know what sine x is. Oh, I should go different colors here. Come on, Ruder. Should know what sine x is. Sine x is x minus x cubed over 3 factorial plus x to the 5. Well, we've done this, right? We have done this. The generic term is negative 1 to the n plus 1, x to the 2n minus 1 over 2n minus 1 factorial, and it goes on and on and on. This has an interval of convergence of all real numbers. Converges for all x. How do you get yourself a cosine x from a sine x? You take the derivative of this thing. And taking derivatives is something we do well. So this turns out to be negative 1 to the n, x to the 2n over 2n factorial. It's got the same interval of convergence because we take the derivative of a function that converges for all x, or a series that converges for all x. You also should know that e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus and so on. The generic term is x to the n over n factorial and so on. And this, of course, has an interval of convergence of all real numbers. This converges to e to the x for all x. So what do we do with this stuff? Well, construct power series for cosine of radical x and e to the x minus e to the negative x over 2. Well, that's not terribly difficult. None of that is terribly difficult. What do we know? We know that cosine of x is this green series. So cosine of radical x is what we get when we put a radical x here, 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 and so on. So that's 1 minus radical x squared over 2 factorial plus radical x to the 4th over 4 factorial, sorry, minus radical x to the 6th over 6 factorial, and so on. That's a power series. This other one, this thing, so how does this work? So this is 1/2 the series for e to the x minus 1/2 the series for e to the negative x. Well, the series for e to the x is this one. And the series for e to the negative x is what we get when we substitute negative x, substitute negative x, substitute negative x. So that's 1 plus negative x plus negative x squared over 2 factorial plus negative x cubed over 3 factorial, and so on. Well, what happens when we subtract those? Well, you get a 1/2 and a negative 1/2. They cancel. You get an x over 2 and an x over 2, that's x. And then the x squared terms cancel, but then you get x cubed over 3 factorial. And this continues. The even terms drop out, the odd terms remain. You can make a power series using previously existing power series, which is super cool because approximate the integral from 0 to 0.1 of e to the negative x squared dx within 10 to the negative 8. So let's just be clear. We don't know how to do that, right? We don't know how to take this integral. There is no way that we know of to integrate e to the negative x squared using any elementary functions. But we know that e to the negative x squared is what you get when you go to this slide and you say, that's a negative x squared, so that's a negative x squared, so that's a negative x squared, so that's a negative x squared. That's a negative x squared. That's a negative x squared. Then negative x squared squared. Then negative x squared cubed, and so on. So what are we trying to do? We're trying to integrate 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial, and so on, dx. Well, how do you do that? This is fundamental theorem of calculus. We take an antiderivative, little bit trickier here, little bit trickier here, but that's the idea. Evaluate between 0 and 0.1. Well, substituting 0, that's easy. So our integral value is just what you get when you throw a 0.1 in there. 0.1, 0.1, 0.1, 0.0, 0.1. We're supposed to approximate within that tolerance. So what does that make us think about? Well, this is an alternating series. Alternating series, when we cut them off, are within the first term we leave out of the actual answer. So we find the first of these terms that's less than 10 to the negative 8 and cut off right before there. It turns out that this term is the first one that's less than 10 to the negative 8. So we cut off we cut off there. We cut off there. And we add up these three terms. And these three terms are approximately 0.0996677. That's the approximation within 10 to the negative 8. So Taylor series let us do things that we could never have done before. One more, and I know that I am breaking my unwritten rule of holding them to 10 minutes, but it's not enough to go 20 with a second video. Find the limit as x approaches 0 of sine x minus x plus x cubed over 6 divided by x to the 5th. Now, we could do this with L'Hopital's rule because the numerator goes to 0 and the denominator goes to 0, and that's an indeterminate form. We could do this with L'Hopital's rule. Or we could do this with series. Sine x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus and so on minus x plus x cubed over 6 over x to the 5th. Well, take a moment to think about what happens here. The x's, 3 factorial is 6, and you got this thing. You've got all of these terms divided by x to the 5th. Well, divide by x to the 5th, divide by x to the 5th, divide by x to the 5th. Well, what happens as x goes to 0? As x goes to 0, all of these terms are 0, and so you're left with 1 over 5 factorial, and 5 factorial is 120. 5 times 4 times 3 times 2 times 1 is 120. That's your limit. You can do that without appealing to L'Hopital. So these are some of the ways that we use Taylor series to accomplish purposes that other things can do or maybe not. But that's sort of how we end our unit, and I hope that that gives some at the end of it.